Hello, everyone. So first of all, I want to go over the last practice problem that I assigned you last week. The upper surface of a 15 centimeter thick solid plate with a conductivity of 237 watt per meter Kelvin is being cooled by water with a temperature of 20 degrees Celsius. The upper and lower surfaces of the solid plate are at 60 and 120 degrees Celsius respectively. What is the water convection transfer coefficient and water temperature gradient at the upper plate surface? And this water temperature gradient means the change of temperature in vertical direction at the upper surface of the solid surface inside the fluid. So dt over dy or dx, whatever that we call this direction. Okay, this direction. I'm trying to draw a straight line. This direction. Okay. Now, first of all, you need to read the properties from the table, the table of physical properties or thermodynamic table at the end of the book. So at what temperature? The thermal conductivity of the solid plate is given in the problem statement. But what about the water? Why do we need the water? Because we are going to use that equation that gives us the heat transfer, convection transfer coefficients based on the general equation, correlation between convection and conductivity inside the fluid. So at what temperature we need to read the properties? Whenever you deal with external flow, the flow that is not bounded in all directions by the walls and solid surfaces, you need to use a film temperature. What is film temperature? Film temperature is some average temperature of the fluid. So typically we use this average. The temperature of the surface plus the temperature of the fluid far from the surface divided by 2. So average of the temperature, average between the temperature of the surface and the fluid temperature. That is 40 degrees Celsius. So at this temperature, we go to table A15 and read the conductivity of the water. Conductivity. So we want to know the conduction properties, conductivity properties of the water. 0.631. This is a small number. This is not a very large number. I mean, it says it's still larger than air conductivity, but it's still large, but it's a very small number compared to copper or other metal substances. Now, we write the energy balance. So at the surface, this is a steady state condition, right? So nothing changes because we are not given any information about temporal change of the condition. That's why we assume that the condition is a steady state. Again, a steady state means nothing changes versus time. So if we focus at the surface in here, so lower temperature, it says that the lower temperature is 120 and upper surface temperature 60. As a result, since lower temperature is larger than upper temperature, the heat flow, the flow of thermal energy is from lower side to the upper side, because you know that always naturally the heat transfers from upper temperature to lower temperature. So this is a direction of the flow, right? Inside the wall, inside the solid surface, we have conduction. Outside, we have convection. Okay. Now, if this is the case and we have a steady state condition, let's say you want to focus on this part of your problem and you consider it as your control volume. You remember that control volume is imaginary volume or imaginary part of your system or imaginary room or a space that is separated from the remaining part of the universe. Okay, so if you look at, I just take it out and put it in here. So okay, you remember that we show the control volume boundary that is typically shown by, demonstrated by dashed line. So what is getting into this control volume? Conduction. What is going out? What is the form of energy outlet? Is convection. So conduction is coming and convection is leaving, right? This is a steady state situation. It means nothing changes versus time. So we don't store more energy than we already have inside our control volume. So whatever that we receive, we need to release. Whatever we gain, we need to give to the surrounding. So whatever amount of conduction it transferred toward the inside of this imaginary volume is, must be equal to whatever that is leaving in the form of convection. That's why the energy balance for the control volume on the upper surface in this form. More specifically, I'm using control volume at the surface. So I imagine a very thin layer of nothing at the surface. At the interface between the solid surface and the fluid, this is my control volume. Since this is a thin layer of nothing, some imaginary very thin layer, then it cannot store anything. So whatever that comes in should be whatever that is leaving. That's why conduction toward this surface must be equal to the convection toward outside. Okay. So this is the energy balance that I have. Conduction is coming from lower surface and convection is leaving because the surface is hot, so it releases energy to the water. So this is the overall flow of the heat. So whatever that is flowing inside the wall in the form of conduction must be equal to the whatever that is flowing inside the fluid in the form of convection. This is the energy balance, okay, at this surface. Now, we have this energy balance. Conductivity is equal to K times higher temperature minus lower temperature divided by thickness of the wall equal to convection, that is equal to H times Ts1 minus T of the fluid. Here, guys, when I'm trying to make the, you remember, whenever, let's write it in this one, Q in equal to Q out. You remember, whenever I use this form of energy balance with subscript, your terms must be positive. Your terms must be positive. So this is like I'm writing E in is equal to E out. So I calculate the amount of energy toward the surface and the amount of energy that is leaving from the surface, at the surface, okay? The amount of energy inlet, its magnitude is this. The amount of energy leaving in the form of convection, its magnitude is this. So the magnitude of the conduction must be equal to magnitude of the convection. That's why I put the higher temperature in here and lower in here. So you need to write Ts2 minus Ts1 divided by thickness. T of the surface that is higher than T of the infinity. Okay, so you need to calculate positive value in here. By this equality, I can calculate H. So H is this. Now, we are asked to calculate the temperature gradient at the surface. How do we calculate the temperature gradient? We get back to this equation that we had in this lecture before, in the previous lecture. So H is equal to minus sign K of the conductivity of the fluid temperature gradient at the surface at y equals 0. So this is y direction. This is y equals 0, that level. So this is my y. Divided by Ts minus T infinity, I have T surface, I have T infinity, I have conductivity of the fluid. I read that from table A15. And H value, so temperature gradient is calculated. So temperature gradient is negative. What does that mean? It means as we move in the positive y direction, the temperature is decreasing, and it makes sense because the temperature of the surface is hotter than temperature of the water. So temperature closer to the surface is larger. Now we're going to go to, so we already talked about general form of convection heat transfer equation, very general. And this equation is very useful. Okay, this is a general equation for convection heat transfer. Now, for external flow and even for internal flow, there are so many thousands of equations developed by different studies, experimental and numerical simulations and measurements. Gives us a large number of equations that we can calculate the H for certain geometries and certain thermal conditions. So the purpose of this lecture is this, to use those equations. We cannot put all the equations in here. As I said, there are thousands of, hundreds and hundreds of equations for H. One of the parameters that we typically see whenever we look at the correlation for H is Prandtl number. Prandtl number is another dimensionless number, like Reynolds number. What is the meaning of that? Prandtl number is equal to kinematic viscosity divided by thermal diffusivity. So it can give us the meaning behind that, right? The Prandtl number tells us what is the ratio of diffusion or the speed of the spread of momentum effect versus the spread of thermal effect. That's what its meaning is. And I'm going to talk about it a little bit more in the next slide. Or also is equal to mu dynamic viscosity times C sub P, specific heat, divided by conductivity. Prandtl number is also tabulated at the end of the book for different fluids at different temperatures and different thermal conditions and pressures. For liquid metals, the Prandtl number is very small. For gases is larger. For water is at moderate level. For oils are very large. For light organic fluids is at, again, moderate level. So what does the Prandtl number really means? So when we have boundary flow, boundary layer, let's say this surface is stationary and you have air or water flowing over the surface. As a result, as a result of the friction and viscous effect between the surface and the fluid, we have distribution of velocity. So velocity changes from the surface that is equal to 0 to the free stream velocity. What is the free stream velocity? Free stream velocity is the velocity of the fluid just before heating the surface, uniform velocity. This is called, let's say, V, or U infinity. So it changes from 0, velocity changes from 0 to V. So we have velocity distribution. This is the velocity profile at this specific X location. So you have boundary, oh, sorry, have to. So you have velocity boundary layer. So for example, at this point, at this specific point, the velocity changes from 0 to the original free stream velocity, that is U infinity. At this point, it changes from 0 to free stream velocity over this thickness. Okay. And also, let's say the temperature of the fluid is 20. The temperature of the surface is 50 degrees Celsius. Also, since there is a temperature difference, there is going to be thermal boundary layer developed. Thermal boundary layer developed, and I show it by different color. So temperature closer to the surface, for example, is going to be hotter. Away from the surface is going to be closer to the 20 degrees Celsius. Right. So also we have thermal boundary layer developed. I have to withdraw it again. And they don't have the same thickness. The thermal boundary layer can be thinner or thicker than velocity boundary layer. This thickness, the relative thickness, the ratio of the thickness of the thermal boundary layer and velocity boundary layer can be expressed somehow by Prandtl number. Is a correlation, can be calculated using a correlation in which we use Prandtl number. So it's correlated with Prandtl number, these thickness. Basically, it tells us the velocity boundary layer is growing faster than thermal boundary layer or vice versa. So is the thermal boundary layer growing faster than velocity boundary layer, or velocity boundary layer is growing faster and is thicker than thermal boundary layer? This is the main meaning behind Prandtl number. Again, we're going to use Reynolds number. So as we had for internal flow when we calculated, when we were calculating the pressure loss and friction loss inside a pipe, also for external flow, flow over flat plates, you need to calculate Reynolds number to see if we have turbulent flow or laminar flow. So, but in here, because in internal flow inside the pipe, for circular cross section, the critical Reynolds number was 2300. Here and above 4000, the flow was considered to be turbulent. Here is different. The critical Reynolds number for external flow is 5 times 10 to the 5. So as long as the Reynolds number is smaller than 5 times 10 to the 5, your flow is laminar. Your flow is laminar. And larger than 10 to the 6 is considered to be turbulent. So larger than 5 times 10 to the 5, you don't have 100% laminar flow. How do you calculate the Reynolds number? Reynolds number is calculated here. So again, as density times velocity times x. So this is the, this is not v sub x. X is a location. Okay, so x, rho v x over mu. X is the distance from the leading edge. Okay, the location at the flat plate where you want to calculate the Reynolds number. So V, this is actually V times X over mu. Density times V times X over mu, or V times X over mu. As I said, 5 times 10 to the 5, but the actual value of engineering critical Reynolds number for a flat plate may vary somewhat from 10 to the 5 to 3 times 10 to the 6, depending on the surface roughness, the turbulence level, and the variation of pressure along the surface. But for now, we assume that if the flow has a Reynolds number smaller than 5 times 10 to the 5, then the flow is laminar. So how does it affect the convection transfer coefficient? This is how it affects the convection transfer. Interestingly, if you have only laminar flow, the turbulent, the convection transfer coefficient decreases as we move along the surface, along the x direction. Convection transfer coefficient decreases. At the point where we reach the critical Reynolds number, the flow starts to become more turbulent. So we're going to have more fixing, more mixing, and as a result, there is going to be better heat transfer. The heat transfer is going to have better performance. So heat transfer is enhanced and the convection transfer increases. Then again, when we reach the fully turbulent flow, the heat transfer coefficient decreases. So we have increased, as long as we are in the same regime of the flow, laminar or turbulent, by moving further along the flat plate, the convection transfer coefficient decreases. But as we switch from laminar to turbulent flow, the convection transfer coefficient has a jump in value and it increases. This is, by the way, local heat transfer coefficient, is not laminar. Is not average, is local heat transfer coefficient. There are so many correlations and there are so many equations to calculate, as I said, the heat transfer coefficient or Nusselt number. And as you remember, instead of using H, you use dimensionless form of convection transfer coefficient that is called Nusselt number. If you have a laminar flow, so you calculate your Reynolds number and it is less than 5 times 10 to the 5, and the Prandtl number for your fluid at the temperature that is given to you at the film temperature, again, at the film temperature, is larger than 0.6 for that fluid, then you can calculate your Nusselt number using this equation. If your Reynolds number larger than 5 times 10 to the 5, so it means it's not laminar anymore, and is less than 10 to the 7, and your Prandtl number falls in this range, then you use this equation to calculate Nusselt number. By the way, these equations are only giving you local value. So, for example, if you are in a laminar flow and your Prandtl number is larger than 0.6, this equation gives you the heat transfer coefficient, for example, at this specific x or at this specific x. So it's changing because x is changing, and the same for turbulent. So it gives you turbulent heat transfer coefficient at a specific points. It depends on the x value. But typically, when we have engineering application, when we want to calculate a Nusselt number, heat transfer coefficient, we deal with average value. We want to know the value of the heat transfer coefficient over entire length of a surface or plate. And more importantly, these two equations are only valid for the case of having constant surface temperature. So the temperature of the solid surface is isothermal, is constant over the entire length. Let's say 120 degrees Celsius, 20 degrees Celsius, or 30 or 50 or whatever temperature that is. These are the local values of Nusselt number from which you can calculate the local values of H for isothermal surface only. Now, as I said, we typically need a value of Nusselt number over certain lengths or heat transfer coefficient because we want to calculate the heat rate over entire lengths. So we need average value. The average value for those equations in the previous slide are these. So these two equations, again, are for laminar and turbulent in these two conditions. So first you need to calculate Reynolds number. If your Reynolds number, based on the length of the plate or based on the location at which you want to calculate, up to which you want to calculate heat transfer, is less than 5 times 10 to the 5, then you use these. If the Reynolds number is larger than 5 times 10 to the 5, so it's not laminar anymore, and it's smaller than 10 to the 7, you use this equation. But the question is, what if I have a flat plate? So I have a flat plate, and the length is whatever. So this is X direction, some L value, 10 meter, 20 meter, 1 meter, 50 centimeter, or whatever that the length is. You calculate the Reynolds number based on entire length of the surface. So you are, and the temperature of the surface, let's say, is 20 degrees Celsius. So we have isothermal surface. You have constant or uniform temperature condition. And now you're asked to calculate the Nusselt number and heat transfer coefficient and overall heat rate. When you calculate the Reynolds number, if the Reynolds number, let's say, is 5 times 10 to the 6, what does that mean? It means based on the entire length, your flow is turbulent. So at certain point, you have a transition from laminar flow to turbulent flow. But you don't have turbulent flow right at the beginning, right? So up to certain, because you see Reynolds number is a function of X, density, velocity times X divided by kinematic viscosity. So as X increases, the Reynolds number also increases. That means not from the beginning your Reynolds number is very large, corresponding to turbulent regime. Or in other words, up to certain point you have laminar flow. Then you have transition to turbulent. Then from certain point forward, you have fully turbulent flow. So you have turbulent, transition from laminar to turbulent, and laminar flow. So when you want to calculate the heat transfer rate over the entire length, you need to deal with 3 regimes of the fluid. Or if you want to simplify it, you have to deal with at least 2 regimes of the fluid. Let's assume the laminar to turbulent regime change. happens over one point. That is not the case, but just for the sake of simplification. So whenever your Reynolds number is larger than 10 to the 5 times 10 to the 5, and you want to calculate the average overall heat transfer coefficient, then you need to deal with both regimes. That's why you need to use an equation that is valid for the case of having a mixture of turbulent and laminar flow. So this equation can be used as an average if you have turbulent flow over entire length of your surface. That is not the case. You can use it with some approximation. You can say that, so the whole length is very large, so the laminar part is very small compared to the turbulent part. So turbulent part is dominant. So you can use this equation for the entire length. But for better approximation, you should use this equation because this accounts for both laminar part and turbulent part. For isothermal surface, where we have combination of laminar and turbulent flow. Also, we have, as I said, we have thousands of equations. There are thousands of equations, and we just deal with some basic ones for flat surfaces, or basic the equations for basic geometries. So what if instead of uniform heat temperature, you have uniform heat flux? If you have uniform heat flux, then your local value of laminar Nusselt number and turbulent Nusselt number can be calculated using this equation also. If it is a uniform heat flux, then you can easily calculate your total heat rate, right? Just multiply the heat flux times the area. By the way, these two equations are for local, not average values, right? Then at each location, so this is overall heat rate over entire surface. At each location also, your heat flux that is given, because it's uniform heat flux case, so you have the heat flux, is equal to local heat transfer coefficient times temperature of the surface minus temperature of the fluid far from the surface. This is called Newton's law of cooling, you remember that. According to this, you can calculate the temperature of the surface at each X location. Let's solve an example. Defrosting ice from an automobile windshield. To defrost ice accumulated on the outer surface of an automobile windshield, warm air is blown over the inner surface of the windshield. Consider an automobile windshield that has a conductivity of 1.4 watt per meter Kelvin with an overall height of 0.5 meter. So this height is 50 centimeter. Let me use different color. So this height is 50 centimeter, 0.5 meter. And thickness of 5 millimeter. The outside air that is at 1 atmosphere has a temperature of minus 20 degrees Celsius, and the average airflow velocity over the outer shield surface is 80 kilometers per hour. So we assume that the flow of the air over the surface is like in this direction. Some approximation. Okay. While the ambient temperature inside the automobile is 25, so inside the automobile is 25 degrees Celsius. What is the value of the convection heat transfer coefficient for the warm air blowing over the inner surface of the windshield necessary to cause the accumulated ice to begin melting. Assume the windshield surface can be treated as a flat plate surface. So first of all, we want to assume that and also is very important. So you see, this is the schematic of the problem. So inside temperature is 25. The conductivity of the windshield material is given. Outside temperature is negative -20 degrees Celsius. The thickness is given. What is the temperature of the outer surface of the windshield? If you want to begin melting the outer surface of the windshield must be at 0 degrees Celsius, right? Because we want to start melting the ice, defrost the ice. So this is very important. Negative -20 degrees Celsius, 0 degrees Celsius at the surface, inside is 25 degrees Celsius. Let's see how we solve for this problem. First of all, we assume that you have a steady state heat transfer and one dimension. So you have heat transfer in this direction and the flow is constant at this part, and at this part. So we have a uniform flow of heat. Also, as I said, is a steady state. Thermal properties are constant. So we are given some properties, constant conductivity, and we're going to calculate the convection transfer coefficient. Typically, we assume these, we make this assumption because the thermal conductivity and other properties, they changes with temperature. But we assume that those are the values at some average temperature of the system. Heat transfer by radiation is negligible. So we don't consider the radiation toward the outside, radiation from the sun, radiation from the inner surface toward the interior of the car. The outside air pressure is 1 atmosphere. And also, as I said, the critical Reynolds number is 5 times 10 to the 5. You need to read the properties. Again, if you want to read the properties, when you want to read the properties, you go to the end of the book tables. And for air, you need to look at some average temperature that is called film temperature. The temperature of the surface, outer surface of the windshield, that is 0 degrees Celsius, plus the temperature of the outside air divided by 2, -10 degrees Celsius. At this -10 degrees Celsius, from table 822, you read these values: conductivity of the air, kinematic viscosity of the air, and the Prandtl number. Why Prandtl number? Because we need to use it to calculate the Nusselt number. So first we need to calculate the Reynolds number. What is Reynolds number? Velocity times length of the shield divided by kinematic viscosity. So this is the Reynolds number on the outer surface of the windshield, 8.875 times 10 to the 5. This is already larger than 5 times 10 to the 5 and is smaller than 10 to the 7. It means the flow is a combined laminar and turbulent flow over the windshield. So we need to use a proper correlations for the Nusselt number, the average Nusselt number, because we need to calculate the average heat transfer coefficient on the outer surface of the windshield. So this is the equation that we have. Again, guys, so let's look at the previous slide. So we assume that we have isothermal surface. We use this equation, not this or this, because this is only for laminar flow. This is valid if for most part of the surface you have turbulent flow. But a Reynolds number tells us that for part of the windshield we have laminar flow and part of that turbulent flow, and our Prandtl numbers also falls into this range. Between 0.6 and 60. So we use this equation, laminar and turbulent mixture. And this is going to be our Nusselt number. So Nusselt number at the outer surface, this is a Nusselt number at the outer surface of the windshield. 1131, this is a pretty large number. Now, the convection transfer coefficient at the outer surface is equal to, because Nusselt is equal to HL over K, so convection transfer coefficient is calculated as this. Now, we are asked to calculate for convection transfer coefficient that needs to be provided by the warm air blowing over the inner surface of the windshield. Because this is what we can control. This is what we can design for the car. So for the heating system of the car, for defrost system. So H sub I, H convection transfer coefficient inside is our interest, is very important. To calculate this, we use the energy balance, okay, or we can use the thermal resistance concept here. How? So this is my windshield. So let's draw the thermal resistance. I have one thermal resistance against convection, one thermal resistance against convection, and one thermal resistance again against convection inside. So I have temperature infinity inside. At this node, I have temperature infinity outside, O T sub infinity O, T sub infinity I. Here I have temperature at the outer surface, Ts sub O, T sub SO. Here I don't really know the temperature, Ts, T sub Si. This is my thermal resistance network with 4 nodes. Okay, so I'm asked to calculate this H. For this one, my thermal resistance is 1 over H sub I times area. For this, 1 over H sub O area. And for resistance against conduction, it is thickness over conductivity of the windshield times area. So I have 3 resistances, 1 over A sub OA, 1 over A sub IA, thickness over KA. Okay. And you remember that since it's a steady state, the flow, let me get back to here. The flow here is the same as the flow inside, the same as this flow. So all these flow are the same. And remember that it doesn't matter which nodes we select to write the heat transfer rate based on. So here, the heat transfer rate based on the node at the outside and temperature of the surface is equal to the heat transfer rate based on the temperature at the surface and temperature inside of the car divided by total resistance between these two nodes. I want to draw these nodes and thermal resistance circuit in here. T infinity I, TSI that I don't have access to, TSO that we know the value of, T infinity O. So this equation, the left-hand side, is based on these part of the thermal resistance, and this equation is based on this part of the resistance. So you see, I'm sort of escaping TSI. I don't really need TSI. So the flow over this part must be equal to the flow over this part. What is the flow? Is heat transfer rate. Since the area are the same, they just cancel out. That's why you don't see area in here. So this Q that is equal to TSO minus T infinity I divided by this resistance from this resistance is equal to T infinity O minus TSO divided by total resistance between these two nodes. That is only one thermal resistance. So according to these, A sub I is calculated. And this is a practice problem that you are assigned to submit the solution of. Water at 43.3 degrees Celsius flows over a large plate at a velocity of 30 centimeters per second. The plate is 1 meter long in the flow direction, and its surface is maintained at a uniform temperature of 10 degrees Celsius. What is the steady state rate of heat transfer per unit width of the plate? So this is your assignment. Thank you very much.